Hello and welcome to this module. In this module, we are going to talk about practical topics in Bayesian statistics. So let's get straight into it. So in this section, we are going to talk about selecting priors and commonly used distributions, constantly updating beliefs, online learning, building an hierarchical model, conjugate priors, a complete application project. In this module, we are going to talk about selecting priors and commonly used distributions. So let's get straight into it. So in Bayesian analysis, before data is being observed, we can model unknown parameter as a random variable which represent our prior belief about the value of this parameter. These parameters are called priors. And the distribution in which these parameters are used are called prior distribution. A prior distribution of a parameter is a probability distribution that represents your uncertainty about the parameter before the current data are examined. To carry out the Bayesian inference, we use posterior distribution. Multiplying the prior distribution and the likelihood function together leads to the posterior distribution of the parameter. In Bayesian inference, we must choose a prior distribution, then apply data to get our posterior distribution. We cannot carry out any Bayesian inference or perform any modeling without using a prior distribution. A prior can be determined from past information such as previous experiments. So we have two types of priors. One is objective and second is subjective. Different rules for selecting priors have been suggested in the literature for selecting Bayesian priors. And we have this two main broad categories. The prior distribution that have minimal impact on the posterior distribution, such distribution is called objective priors. We can also name this prior as uninformative or flat prior. As we know that posterior can be calculated by multiplying or the multiplication of prior distribution and likelihood function. So posterior is equal to prior into likelihood. Objective priors describe general information about the parameters. It let the data influence the posterior the most rather than the prior. That is why likelihood function often yields more information than the uninformative prior while computing posterior probability. Posterior is equal to likelihood. The posterior distribution is always equal to likelihood function if we are using uninformative priors. The simplest and oldest rule for determining an uninformative prior is the principle of indifference, which assigns equal probabilities to all possibilities, which is also called as uniform prior. Let's take an example of objective prior. With the help of example, consider a situation in which one knows a ball that has been hidden under three of the cups A, B, and C. But no other information is available about this location. If no information or data is present, then we will set the prior as uniform prior, that is equal value in all the cases. In this case, a uniform prior of probability A is equal to probability of B equal to probability C is equal to 1 by 3. Seems intuitively like the only reasonable choice. More formally, we can see the problem remains the same if we swap around the labels. More formally, we can see that the problem remains the same if we swap around the labels A, B, and C of the cups. It would therefore be odd to choose a prior for which a permutation of the labels would cause a change in our prediction about which cup the ball will be found under. The uniform prior is the only one which preserves the invariance. Subjective prior is selected based on the domain knowledge or intuition or perhaps from the result of previous analysis. They are called subjective priors. A subjective priors allow the practitioner to assert their own views into the prior. It expresses specific, definite information about a variable. Subjective prior is also known as informative priors. Say we perform a Bayesian analysis and get a posterior. Then we get some new data for the same problem. We can reuse the posterior from before as our prior, and when we run Bayesian analysis on the new data, we will get a new posterior which reflects the additional data. We don't have to redo any analysis on the data from before. All we need is posterior generated from it. This prior can be the posterior from another problem or just come from domain knowledge. Let's understand subjective prior with the example. We investigate the value of data by conducting an experiment where we could flip the coin 10 times and calculate the proportion of times the coin lays on heads. Up here, we observe 4 out of 10 of the tosses of the coin. Set the parameter of beta distribution as probability of getting head to be 0.5. That we will set the parameter as beta 30, 30, which will concentrate to our probability equal to 0.5. This mathematical express our belief about the parameters called prior distribution. We can qualify the result of our experiment using a likelihood function. In this case, we have used binomial likelihood function for theta given 4 heads out of 10 coin tosses. Likelihood equal to binomial 10, 4 theta. Bayesian analysis allows us to update our belief about the parameters with the result of our experiment. In simple cases, we use or we compute a posterior distribution of the parameter by multiplying prior distribution and likelihood function. In this example, the beta distribution is called the conjugate prior of binomial likelihood function because the posterior distribution belongs to the same distribution family as the prior distribution. So posterior is equal to beta 4 plus 30, 10 minus 4 plus 30. Here we have the posterior distribution of the theta with prior distribution and likelihood function. Here we see the posterior closely resemble to the prior distribution. This is because we have used informative prior. And this is how subjective or informative prior can be used to predict posterior.